Hello, I am Ricardo, and I'll be presenting our vision paper that is a result of an ongoing collaboration with Razan, Alessandro, Patrizio, Danny, and Thorsten. In this paper, we argue in favor of using specification patterns to map properties of control theory and software engineering. To build our argument, I will describe the gap between the two disciplines with an example inspired in the engineering process of Ferrari Scuderia. Then, I'll detail our solution idea and illustrate how to apply it in a concrete example. Finally, I'll outline opportunities for future work. We learned from the keynote on engineering software at Ferrari Scuderia, presented by Claudio Silenzi at ICSI 2015, that the engineering process in Ferrari is divided in one-week sprints, in which engineers with different expertise must analyze, produce specification, code, test, and validate the racing car. Engineering at Ferrari means developing software that should work on high-performance racing cars operating in safety-critical environment that must be in constant evolution. By the time of the keynote, the controlling software of the ECU had around 30,000 tuning parameters that were changed in between races. The engineering process begins with the design of the control specifications. With the specification in hand, the control engineers model the controller in Simulink and do code generation. Here, the techniques that they used should guarantee that the system is correct by design. Then, software engineers get the generated code and work on customizations. And finally, integrate the code into a bigger system. The changes in code before integration raises an important question about this design process. Do the safety requirements considered by control engineers still hold after the software engineering intervention? Seeking for a solution, we need to look deeply into the fundamentals of control engineering and software engineering. On the one hand, control theory deals with continuous dynamics, focusing on smooth and continuous change. The field relies on mathematical rigor and exploits diverse ways of expressing their properties. For instance, using Boolean expressions, first-order logics, or even ordinary differential equations. On the other hand, software engineering deals with discrete dynamics, where the changes are more abrupt. The field relies on tooling for verification of ever-changing systems. Wouldn't it be nice to have both? Correct by design and tooling for validating when the original properties are modified and integrated into a big system. For that, we need to unify or map control theory and software engineering properties. From one side, we have properties such as stability, settling time, overshoot, and steady-state error. From the other, we have safety, liveness, reachability, functional correctness, and many others. How to map them? Mapping these properties is particularly difficult mainly because they are usually represented in different notations. What if we use pattern system? With property specification patterns, we can benefit from using recurring solutions derived from many applications to understand how properties from the two disciplines are related. A specification pattern is defined by a tuple, scope, pattern. Scope is the extent of a program execution over which the pattern holds. An example of scope is after Q, meaning that the pattern should hold for all the trace of execution after the event Q happens. In property specification, a pattern describes a generalized recurring system attribute. An example of pattern is existence, meaning that the system attribute Q eventually holds. It is important to note that in the specification pattern system, the patterns can be composed using nesting operators, enabling a property such as always, eventually, queue holds. More concretely, we want to use the adaptive cruise control problem as an example to illustrate our mapping idea. The adaptive cruise control problem requires that an autonomous vehicle, here named after Eagle, maintains a certain relative distance from the leading car. When Eagle is far from the leading car, its speed is maintained according to the setup. When the Eagle gets too close to the leading car, the spacing control is activated, adjusting Eagle's speed in a way that the vehicles move towards keeping a safe distance. The safety requirement here is Eagle must keep a safe distance from the leading car. Here, we illustrate how we mapped the properties over the adaptive cruise control example. First, we modeled the controller that solves this problem and verified whether the distance between the cars is maintained for a number of scenarios. For this, we used MATLAB and Simulink. Then, we used Simulink Coder to transform from the Simulink model to C code. At this point, we modeled the safety requirement as stability property from the control theory side. From the software engineering side, we used the pattern eventually always safe, meaning that at some point of the program execution, the Eagle car will always be at a safe distance. Finally, we introduced the generated code and the specified property into a model checker and compared the results to the ground truth coming from the scenario simulated in the beginning. By this means, we seal the properties mapping. This is a summary of the mapped properties. On the left side, we have stability as the control theoretic property. Here, stability is illustrated by this graph, conveying that the system attribute is converging to an equilibrium point and is bounded by an acceptance margin. On the right side, we have the eventually always safe, representing a liveness property in the software engineering domain. Here, we illustrate the property with a Bushy automata. The properties were mapped using the globally existence universality pattern. In a nutshell, first we motivate the mapping with the engineering process used in Ferrari Scuderia. Then, we ask whether the safety requirements considered by control engineers still hold after the software engineer's intervention. Then we argue in favor of using specification patterns for mapping control theory and software engineering properties, with the benefit that the controllers will be correct by design and the engineers will have powerful tools for validating properties after change. Our methodology is comprised in 4 steps, where first we do the control design and collect evidence on the model. Then we transform the control model into code using a reliable tool. Then we model the properties using the patterns. And finally, use a verification tool to gain confidence in the mapping. We used as a concrete example the adaptive cruise control and mapped the control theory property stability with eventually always from the software engineering domain. For future work, we want to further identify and map other properties, for instance, settling time, overshoot, and steady-state error, and explore richer and more autonomous systems. Our systematic approach for validating our mapping provides a pathway for building evidence that the mapping is sound. We wish to keep using it. Finally, it is our intention to investigate the topics of this paper with companies providing autonomous systems to validate the robustness of our approach.